Adam's academic brother for about 25 years. And maybe I should Adam's story.
Oh, I think I know this story.
And when I came to Stony Brook, I inherited Adam's office.
Oh, that story. This is a story about when we were playing.
And then, I came to, we had left a few months before, I think a cleaning lady had gone there. And then everything looked tidy enough. And then I started kind of, bringing my stuff in and started opening drawers. And every single one of the drawers, the desk, filing cabinet, had coffee stains in it.
Right, so that was the year of the budget freeze when they weren't cleaning anything. Right, so Jeremy made a rather apt comment about this being a home away from home, and I sort of feel the same way. So it is a pleasure and an honor to be here. And I was trying to think of what the 25 years actually refers to, because I remember coming to what I thought was the inaugural conference for the IMS, and it was in 1988. So that was 27 years, but that was 80. All right, so it's 26 years. But anyhow, so it's quite an honor to be here now commemorating that. Okay, so I want to discuss matings. So this is holomorphic dynamics in one complex variable, and matings is a way, one of many, but a very interesting way of producing rational maps, iterated rational maps out of pairs of polynomials. And it was alluded to, I think, in one slide and one reference in Kevin Pilgrim's talk, but I don't think he elaborated on it. So I'm going to give you the definition, and the definition involves a lot of finger crossing and wishful thinking and invocation of Thurston's theorem, and I'm going to somehow de-emphasize that part and replace it by showing you some movies, which makes the point much better, but I do need to start somewhere. So at some point or another, I need to recall the notion of external rays. So let's talk about polynomial Julia sets. So suppose I have a polynomial of degree greater than 1. And I will consider actually the filled in Julia set. So this is the set of all points such that the orbit is bounded. And then, in case I make reference to it, the Julia set is the boundary of that. So this is the filled Julia set. And it's full. It has no holes. Okay, that's a consequence of the maximum principle. So the typical picture, well, a typical picture would be something like this. And by virtue of this being full, in fact, the definition of it being full is that it's non-separating, and then by the Riemann mapping theorem, there is an essentially unique conformal isomorphism from the exterior of this to the unit disk, the exterior of the unit disk. In fact, actually, I'd like to think of it going the other way. So here I have the closed unit disk, which I remove, and here I have this, filled Julia set, say, which I remove, and I can map the complement of this to the complement of this, sending infinity to infinity in an essentially unique way, just up to a rotation here, and there's a natural normalization that will send sort of the positive real axis to a curve which is asymptotic to the positive real axis. All right, so I'll just imagine that normalization at all times. And then using this conformal map, I can transport the obvious polar coordinate system of the complement of the exterior of the unit disk over to the dynamical plane. So I have these concentric circles here. which are mapped to curves. They're equipotentials. They're level lines of the corresponding Green's function. And then there are the radial lines here. So these are orthogonal family of curves, and the images of these are called external rays. And things look like this. Right? And it's a simple fact that probably everyone here knows that actually this conformal map actually gives an analytic conjugacy between, if this is the polynomial of degree d, between z to the d over here and your given polynomial over here. Okay, now, notice I stopped short of drawing these rays. I mean, they get closer and closer to here, and I'd like to just do that, right? But of course, a priori, I don't know, because possibly a ray will do that. And this is precisely the issue of whether or not this Phil-Julius set is locally connected. So here in hence, okay, so I'm going to assume, I guess if I haven't said so, I'm assuming I haven't said so, but I've implied so, that I'm focusing on the case where the Phil-Julius set is connected. And I also want it to be locally connected. Sorry?
The boundary is locally connected.
Actually, it's the same. But yeah, as you like. K will be locally connected if and only if the boundary is. I'm not going to give the definition of local connectivity, but the Theodore theorem, by the Theodore theorem, it's equivalent to the Riemann map going in this direction, extending continuously all the way up to and including the unit circle. Okay, so we're banning this, which means that the Julius set, the boundary of this, actually is represented in a canonical way, suitably compatible with the dynamics, as a quotient of the unit circle. Okay, so, all right, so huge amounts of the theory of polynomials, of polynomial Julius sets, is based on all various partitions that one can get using collections of rays and equipotentials. There's Yoko's puzzles and so on and so forth. So there's something fun you can do. Now this is, I believe it's Dua D. Hubbard. The first mention of this is in an asterisk note. I believe it's the first mention is in an asterisk note of Dua D, or it might be in an ICM proceedings article by Dua D, I forget. But my recollection, my understanding is that this was this observation was the product of a excited, heated discussion amongst Dua D and Hubbard in, is it Café des Ursulines? Perhaps? Yes. So, in fact, I believe that the construction that I'm about to, in fact, to this day, we don't know of this as a construction. It's a wishful thinking construction which can be implemented in various tame cases. But I believe that this was proposed as an explanation of certain of the uncanny appearance of certain structures in parameter spaces of rational maps, for example, Mandelbrot sets, coming up in an unexpected way. And the explanation was, perhaps the corresponding Julius sets can be understood as having arisen in the following way, which is a little bizarre, but is rather fun. So I imagine that I'm given two of these. So I put one over here, and let's have one with some interior. And I really want to think of these at the moment. Each one lives in its own complex plane. Okay, and each one has its corresponding system of rays and equipotentials. Like, I'll just draw in the rays at this point. So I guess rays will be purple for the purpose of this talk. Interesting thing about rays, if I haven't mentioned it already, is that there will typically, in fact, they can sort of all but one example, be ray pairing. So there are two accesses to this point here, and by general theorems in complex analysis, each access will contain a ray, and rays land by assumption. So I've got a ray coming in up here and a ray coming in up here, and maybe here I would have that many rays. All right, but I have these two separate complex planes, and now I say, what happens if I put them together? Okay, so there's various ways of talking about this formally, and one of the ways I like, actually, this symbol has appeared before. I think we owe it to Jack. This is a latex symbol. If you take the complex plane and you compactify it, not by putting in the point of infinity, but by putting in the circle of directions in the natural way, then you get a topological closed disk, which we denote by / copyright symbol or whatever it's called. So actually, maybe I should have given these more distance here. So really, I think of this one here as having a sort of visual circle at infinity. And of course, these rays are in natural bijection to the points on the circle of infinity. So here's one, and then here's my other one. All right, and here, let's say the fundamental theorem of plane topology, let's say, is if you take two copies of the closed disk and you identify the boundary circles, then you get a topological sphere. And if you identify the boundary circles in an orientation reversing way, then this topological sphere carries a natural orientation. Okay, so we're going to do that here. We're going to identify these, in fact, by sending theta over here. So here's a ray that comes in with angle theta. And we're going to match that to the ray, actually of minus theta, because I want something orientation reversing. And I just do that all over the place. Okay, so what I get is a topological sphere with an equator, right? This curve glued to this curve. And then in the northern hemisphere, I seem to have lost my dendrite. All right, so in my northern hemisphere, I have this one. And in my southern hemisphere, I'll try to draw them to look a little different. I have this one. And I have rays from the upper hemisphere, longitude lines coming down from the upper hemisphere, and then continuing, indexed by the opposite angle, into the lower half plane. So, for example, I have this ray here, comes down, and it hits the equator, and then it continues on, and for example, maybe lands there. So theta goes to minus theta. But of course, there's also a ray coming from here, so that's going to come down and maybe land. And for all I know, it lands here, and there's another ray coming out here, and then maybe it lands there. So there's some fairly complicated pattern, well, okay, I mean, this is called the formal mating. You just do this. So I make a topological sphere in a somewhat artificial way. I can't claim that this is a Riemann sphere in a natural way. It does have a complex structure up here. It does have a complex structure down here. Okay, but one has to be careful because the complex structure up here actually makes each of these hemispheres into a copy of C rather than a copy of the disk. So it's somehow misleading to think of this completing to a Riemann sphere. We not only have this, but we have some dynamics on it. Because here we had one polynomial, and here we had another polynomial. And what's happening along the circle at infinity, this is precisely where each of these polynomials is conjugated to angle decoupling. At some point I'm going to start focusing on quadratics, so I'll just say angle doubling, but all this is general. So going here along the circle, it's just theta goes to the degree times theta and here it's what I was given, and here it's what I was given, and it all fits together compatibly, and I actually get a branched self-covering of this topological sphere. So that's what's called the formal mating. Okay, it's a dynamical system, but it's not a holomorphic dynamical system. In fact, there are all sorts of obvious reasons why it can't be. For example, the action on rays is going to be, well, I mean, you can think about it. You have expansion along the circle here, and effectively you have a saddle picture all along the equator. So there's no way in the world this is a rational map. But you say, well, I'd like to make a rational map out of this. Okay, so now this is where the heuristic comes in, and making this heuristic precise is harder than it seems. The idea is I've drawn the first few stages of an evident equivalence relation here, where my equivalence classes are chains of external rays, or actually closures of chains of external rays. What do I mean by that? So I start off, let's say, up here, and I have the ray of angle theta and its endpoint, and actually all other rays in the upper hemisphere with that endpoint. And then I continue all those down into the lower hemisphere, up to and including their endpoints. And then I continue, etc. Okay, and I do this for every theta. And this gives me what's called the ray equivalence relation. So we have a topological sphere. So let's just say the formal topological sphere. And we have a ray equivalence relation on that sphere. We have an equivalence relation on a space. Well, why not take the quotient? Now, quotients, of course, have to be considered carefully, but I can at least talk about it. So I have one cannot see that. Well, so I take the quotient space. Effectively, what that means is I'm imagining these things on a balloon, and I just somehow try to pull all of these purple strings tight simultaneously and see what's left over. And whatever it is that's left over, because this process of pulling everything tight suitably commutes with the dynamics, I will get a self-map of the quotient. So first question is, what on earth is the quotient going to be? So if you just start out with some sort of unspecified equivalence relation, you're feeling, if you don't know anything better to say, then you can imagine that your quotient is probably some severely non-Hausdorff space, and then that's the end of the discussion, right? So to even get a Hausdorff space, this equivalence relation has to be what's called, well, monotone. So in other words, let's see, limits of equivalence classes, a limit should be a well, and upper semic. I don't know if it was upper or lower, but so a limit of so a limb soup of equivalence classes should be a subset of a corresponding equivalence class of the limit. Okay, so just getting this to be Hausdorff might be an issue, but we want something better. We would like this to be a Riemann sphere. Why? Because this was part of the heuristic explanation of these parameter space phenomena that Duody and Hubbard were musing about in the Café des Ursulines. Now, exactly what hypotheses need to be made for this quotient to be even a topological sphere, to this day, there's no explicit understanding of that. Okay, but let's ride with this. Let's just be even more ambitious. You say, what if this quotient were not only a topological sphere, but in some natural sense, a Riemann sphere? So I'm going to ask something even more outlandish. Not only should my quotient space be Hausdorff and even a sphere, but I'd like there to be a canonical complex structure which is compatible with the induced dynamics, and something which is invariant. And furthermore, just for everything to be normalized, I'd like it to be a unique invariant structure. Okay, so all of this is built into the definition of mating. To actually say this properly is a talk in and of itself. But if I take the formal sphere, quotiented out by the ray equivalence relation, we would like this to be a sphere with you say unique invariant complex structure, invariant under, well, the map induced on the quotient by the formal gluing of the two polynomials. And if all of these wishes come true, then I say that what I obtain here, which would be unique up to Mobius conjugacy, I call that the mating, or the geometric mating, or various bits of terminology. But it's somehow a two-step process. You first do it formally, you collapse, you get lucky, and then you have the mating. Right. Now, one might think that this is, okay, so there are existence theorems about matings, which I'll mention in a minute, and one might think that this is actually how one proves them, and one would be quite mistaken. Okay, at least the main theorem I'm going to talk about, or the main theorem about this is, well, it's really a combination of results by various people, but somehow in my view, the central part of it is Tonley's thesis, and then there's some follow-through argumentation supplied by Mary Reese and Mitsu Shishikura. So the theorem, at least in the post-critically finite case, okay, so now everything here is with reference to the Mandelbrot set. So following Jeremy Kahn's convention, I will draw only the upper decorations of the Mandelbrot set and not enforce the reflection symmetry. Okay, actually, no, I do need upper and lower ones here because I need to talk about what conjugate limbs are. Okay, so this is a limb of the Mandelbrot set. I don't want to give a formal definition, but it involves looking at external rays for the Mandelbrot set. Well, this is basically the definition, and then the parts that are lopped off. And these are naturally indexed by rational numbers. So this is the 1/3 limb, and this is the minus 1/3 limb, otherwise known as the 2/3 limb. And these two are a conjugate pair. And this is the 1/2 limb, otherwise known as the minus 1/2 limb, and this is a self-conjugate limb. Right? So every point on the Mandelbrot set, this is a theorem in fact, contains a local connectivity statement. Every point in the Mandelbrot set is either in the closed cardioid or in one of these limbs. And let's just ignore the cardioid because this is just Jordan curve Julius sets. There's no pinching going on. So if I'm considering a potential mating, then the two polynomials, either they're in conjugate limbs or they're not. Okay, so the theorem, so this is Tonley plus Reese Shishikura is that, so for post-critically finite, all right, so this is for quadratic polynomials. So two post-critically finite polynomials, both post-critically finite. So the mating, I mean in the strong sense, your geometric mating, the mating exists if and only if C minus and C plus do not belong to conjugate limbs. And if you play around with pictures, the fact that this condition is necessary is not inordinately surprising, because you could imagine taking one of these and its mirror image, and if you go through this process, then you find that you just create all of these ray loops. And pinching off those loops, you're not going to get a sphere, you're going to get a cactoid, a balloon animal. Right? So, I mean, at the bare minimum, to get a mating, we need the quotient to be a topological sphere. And in my terminology, I call that the topological matability condition. So one might imagine a perfectly reasonable heuristic. If you've never seen this before, one might imagine that one proves a theorem of this kind by first doing some sort of combinatorial work, maybe looking at the symbolic dynamics maybe about the partnering relation amongst rays for this one and the partnering relation for these, and then somehow looking in detail at the equivalence relation that the two of them mutually generate, and blah, 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 and showing that first one gets a topological sphere, okay, and then the next day coming in and working even harder to show that this topological sphere carries a nice invariant complex structure. And this is not how it's done. At least not in at least not in these main cases here. In fact, I'd love to see somebody try to do that. Taking fairly easy cases like, say, take the airplane over here and say Cocopelli over here, and to show by hand that you get a topological sphere. I'd like to see somebody do that. So this is not what's done at all. In fact, what's done is quite different. So Tonley in her thesis considers, well, she addresses not quite this problem, but the corresponding problem up to homotopy. This is why the PCF condition becomes essential to that approach, whereby you start with making the formal mating, and then you relax things, and you just think of that as a branched self-cover in the sense of Thurston's theorem, and you study that enough to find out when that is or is not obstructed. There's some fine points because there are obstructions that are removable and so on and so forth, but that's, the experts all know that. And if it's not obstructed, then Thurston's theorem gives you a rational map, which is somehow related to this problem, but you don't know yet that it's a mating because you've forgotten all this structure about ray, but it's a candidate for the mating. At least now you know which one should be the mating. And then this supplementary work can be interpreted as showing that the candidate is a legitimate candidate. Okay, so it's somehow this two-step process. And for me, what's sort of funny about this is that if you're somehow only interested in topological mating, in other words, if you're only interested in proving that what you get is a topological sphere, you've actually gone and done all this extra work to prove that it is P1, and then you observe that P1 of C is in fact a topological sphere. So again, challenge to the younger people in the audience, or the older people in the audience, is take an example. Oh, wait, I mean, we can all do this by hand if I take, say, that one and that one. But try that one and try to master the equivalence relation. Okay, now I owe you some pictures, some movies. Sometimes I start this talk by just showing the movie and dispensing with all of this. So where is my, okay, have to log in again. Right, so this, okay, so all of the movies here are, of course, courtesy of Arnaud Cherita. There's a fine selection on his website. This is the, last one, when it comes up, is the basilica. This one is the basilica mated with the rabbit. Now there's actually more going on here than I've explained. This movie illustrates more, because this is actually not just doing the collapsing, but it's doing the collapsing in a particular way whereby some of this is called slow mating, whereby you think of the equipotential disks here, and rather than doing the collapsing once and for all, you take the equipotential disk, say, this far up in the upper half plane and the corresponding one in the lower half plane, and you just simply cut out this annulus, right? And then you just keep compressing that more and more and squeezing it tight. And then, at least heuristically, in the limit, one is getting the mating. Proving that, of course, actually, I mean, well, anyway, so the thing is that even visualizing this way was not possible, or at least was not feasible, until the work of Bartoli Nekrashevich. So this program of Arnaud and others have, Xavier has made such pictures, Ilyas Zidane has made such pictures. This is really based on ideas of Bartoli and Nekrashevich, which somehow allow you to circumvent what a priori should be analytically borderline intractable. Namely, hidden in this, maybe it's not so hidden in this, we're invoking the uniformization theorem. right? And because things are going on dynamically here, the dynamic somehow takes care of what you might think of as difficult implementing the uniformization theorem. Okay, so that's the basilica and the rabbit. So for those of you who don't know what I mean, the basilica is the center of this component here where you have a super attracting 2 cycle, and the rabbit is the center here where you have a super attracting 3 cycle. There are other movies I didn't bother downloading today where you're mating something with a dendrite or even mating 2 dendrites together. Again, sometimes for people who've never seen this, mating 2 dendrites and getting a topological sphere is perhaps difficult to get your head around, although the movie makes it plausible. But I want to show you another example. So once the obvious examples were made, Arnaud started asking me if I had any weird examples. And there's one I had been studying, which had a longish ray connection. So remember, I've discussed the ray equivalence relation here, and I've not really commented on how long, how many times around I might expect to have to continue crossing the equator until I finally dead end on a point that has no partner ray, right?
Topologically, all you have to check is that this relation is upper semi-continuous and monotone. And then, of course, it says,
well, you have to check. There's more. Okay, that.
No, to obtain a topological sphere, that's it.
Monotone means what for you?
Monotone means the decomposition elements are connected.
Yes.
Semi-continuous.
They also have to be They have to be connected, non-separating, and a fine point which people generally don't bother to mention because it's not a worry in the polynomial case, in the case of the dynamical case. One also has to show that there's more than one ray equivalence class, which for polynomials is more or less evident because you can only have finitely many rays landing at a given point. But believe it or not, I have an example of a topological mating of 2 closed sets where there's 1 ray equivalence class. Okay, and I do not want to display that here. But yes, there's a theorem of Moore.
What?
I mean, already getting a ray equivalence class with interior sounds impossible until one day I just sat down. I mean, there's a trick. But that's not an issue here, right? I mean, all of these, every ray equivalence class here is going to have, a countable, finite or denumerably infinite collection of ray links. And anyway, I mean, that just simply cannot fill up the whole sphere. You could apply bare category, but it's simpler. It's just that the intersections with the circle here will be countable. Okay, so there's a theorem of Moore, which says in full generality, if you have an equivalence relation on the sphere, then the quotient space is a sphere if and only if the equivalence relation satisfies simultaneously all of the following conditions. It should be upper semi-continuous, or equivalently, you just already assume that the quotient is Hausdorff and you move on. The equivalence classes should be closed, should be connected, and non-separating, and there should be more than one. And it's fairly easy to see that all of these conditions are necessary, and the theorem is that they're sufficient. Okay, and again, if one didn't know better, one might think that the way this theorem is proved is to analyze the 2 equivalence relations jointly, invoke Moore's theorem, observe that you get a topological sphere, get a good night's sleep, wake up and find an invariant complex structure. And to my knowledge, there's not a single case that can be interpreted that way. Or there might be, I mean, possibly maybe the Siegel-Diss mating. Where's the?
What is difficult about proving upper semi-continuity, for example? Is that a different?
Well, all right, so give me how do you know that this is only finite? So okay, I'll jump ahead to my other slide for a minute. So in particular. Yeah, well, one question at a time, but yes?
The movie while you're doing the explanation.
Okay.
Let's watch the movie.
Let me address Andre's question. Let me address your question in a minute, because that's the next thing I just want to show you the other movie. Okay? So Arnaud had asked me if I had any more complicated examples for him to try out his skills.
You have to go back to the VLC player if you want to see it. below yours.
Oh, I see. Oh, here it is. So this one here, this involves two period 10 components. And one of them is somewhere in the 1/3 limb way up here, and the other is along here and slightly above the real axis. And well, I mean, these have what I call, these have a long ray connection. How long is, okay, what's the length of a ray connection? So I have one of these ray equivalence classes, and I count not the number of intersections with the equator, because it's easy to make that big just by having, you know, many, many rays landing at a given point. But I look at all embedded arcs, all chains of arcs that I could find in this ray equivalence class, and for each of them, I count the number of times that chain crosses the equator, and then I take the maximum of those, the sup of those, and I call that the length. Okay, and I had to work quite hard to find something. Okay, so there's one, if you mate Cocopelli with the Airbus, the period 4 real component, which is not the tuning of the basilica, then that has a fairly long ray connection. I think length 6 if you measure it the way I said. And you can see that by hand. And I had to work quite hard. I had to write a computer program and then optimize the computer program to find anything longer than that. And I had to go up to period 10. Okay, and then that has length 8. So that's this one here. So this one here, I call this one, this is the mating of the octopus with the hookah. The demarcation between the dark blue and the white, that's the image of the equator. So it swirls around. So all right, I mean, there's all sorts of fun things that one sees in these movies which at the moment defy explanation. Like, why is it that it's only at the very last minute that these hyperbolic components somehow become large enough to see? I don't think anyone's explained that. Also, certain parts of this thing sort of zip together faster than others. This is something about harmonic measure. Somebody could say something about that. There's also a collision going on here because this is becoming, well, whatever. I mean, there's some contact, there's some sort of emergent contact of two components. That actually you can predict from the combinatorics. Okay, let me show you one more picture of that one. This is a much more recent picture. I was nagging various people in Toulouse for years. Can you make a picture that also has rays, not just the equator? So this has some of the rays, but no, this is the same one. Oh, I have to go down here. This is, oh, did this just open another one? This is a different, yeah. So this is the octopus and the hookah with some of the rays. So the black is, so that's the rays getting pulled out. I'd like to see more rays simultaneously in the picture, but it might be too busy. Okay, so moving back to Andre's question, which is actually the question, if one wants to implement this approach here, what's so difficult about this? So I claim that showing that this equivalence relation is simultaneously monotone and closed is a real issue potentially. Here I've just shown you post-critically finite examples, but everything I said here will make sense given any pair of connected, locally connected quadratic Julia sets which do not lie in conjugate limbs. And one might conjecture, so there's various things which were called the mating conjecture, and one of them I call the topological mating. Well, one might conjecture that the conjugate limbs obstruction is the only one, even in generality, without this condition here. Now, that contains a no invariant line field consideration. So one might decide to just not worry about getting it to be an actual honest geometric mating and just think about things topologically. So you might conjecture, and I call this the topological mating conjecture, that if you take a pair of these that are not in conjugate limbs, then the quotient under the ray equivalence relation is a topological sphere. And then one might try to address this by Moore's theorem, and the problem that one faces is precisely, or a major problem that one faces is to show that no ray connection, that no ray equivalence class contains an infinitely long connection. Why is that? Because there's an argument It's not particularly hard to believe once you draw the picture that says that if you have an infinite ray connection, then either the ray equivalence relation is not closed, or it contains a separating equivalence class. For example, suppose that I have my ray, I just draw a caricature without the Julia set. Suppose I come up and I go down, and I come up and I go down, I come up. You say often, well, by compactness, there's got to be some sort of accumulation here. Two possibilities. Possibility number one, this accumulation here is not in the original ray equivalence class. Well, then this ray equivalence class is not closed. Possibility number two, it is in this ray equivalence class, which means it's got to connect up from around the back. One has to make that precise, but that's the only difficulty. And then we have a Warsaw circle type gadget, and this separates the sphere. Okay, so because of this difficulty, I got interested in the question of finding long ray connections and seeing how long I could make them, because if I could do this in a suitably systematic way, for example, finding a pair of mateable post-critically finite maps that have a ray connection of length 10, and then moving, and then suppose I knew that with some confidence that I can move out a little bit in this wake here and a little bit in this wake here, so that I had a ray connection of length 20, maybe one that even shadowed the one of length 10, and suppose I could do that indefinitely, and suppose some other things work right, well then, this would prove that the generic pair of polynomials that are non-conjugate limbs cannot be topologically mated. Right? I mean, a simple bare category argument of which the inductive step is something like showing that every long ray connection is suitably shadowed by a longer one. So in support of this, I tried to do a computer experiment to see how long I could make things. That's when I found this example, and then a master's student of mine who had been an undergraduate of Tan Lei's, heaven knows how he found this. It's literally a needle in a haystack. Where is the, oh, here it is. It's literally a needle in a haystack finding these long ray connections. But, sorry? Who defined what? Who found it or who defined it?
Found it.
Stuart Price. And they're somehow not all visible here at the same time. I don't know why. I don't know what to do here. View, full screen. Well. This is, of course, not drawn to scale, but all right. It's just a picture. But here, if you scroll up here, you'll see the external angles, and they have rather large denominators. This is period 22. Heaven knows how he found it. This has length 12. This is the current world record. Okay, so it does seem that you can find longer and longer ray connections, and it seems that basically the length of the ray connection that you find is perhaps going to be at most the period, and so you're going to have to look an awfully long time to find longer ones. And my conjecture now, just because I like to be contrary, is I conjecture that generically, as you move farther and farther out, non-conjugate wakes, you can find longer and longer things, so the upshot is that most things cannot be mated, but that's just a conjecture. Okay, now I'm already starting to run out of time, so I want to talk about the other aspects. So this work of Tan Lei's dates from about 25 years ago, or maybe more actually, right? So of course, since that time, people wanted to somehow complete this in some way and remove the PCF hypothesis here. And one approach could be summarized as, wouldn't it be nice if the matings whose existence followed from this discussion here, if the mapping that one got, so there's a set of post-critically finite parameters in the Mandelbrot set, and actually, I should say, once you have matings involving a super-attracting point, a center of a hyperbolic component, then a quasi-conformal massage argument shows that you can also get matings with any of the non-super-attracting parameters in that. So in fact, the locus of matings, which are proved to exist by a mild modification of this argument, is looks rather large. It's there's the interior of all of this whole component here could be mated with this component here, and this component here could be mated with this component here. And if you look at the set of pairs of C1, C minus, and C plus, such that the modification of this theorem applies, and you look at the mating operation, you choose a normalization so you get a well-defined map into the space of quadratic rational maps, you could say, wouldn't it be nice if this extends continuously to, well, to where it could? So what you'd like is to be able to extend this to the Mandelbrot set cross the Mandelbrot set minus the set of all pairs belonging to conjugate limbs. That's the most you could hope for. So you say, wouldn't it be nice if the mating operation would be continuous? And well, I guess my point is that, well, too bad it isn't. Okay, so I want to show you, in the time remaining, to summarize a couple of mechanisms that will disabuse you of this notion. So one mechanism, it's almost staring you in the face in the sense that you can actually make it computationally explicit for low periods, and for the period 1 case, which is in some sense degenerate, it was already known. So let me just say, so suppose I have two hyperbolic components. So I have a hyperbolic component, and let's just say that, and another hyperbolic component. This is the hyperbolic component containing C minus, and this hyperbolic component containing C plus. Okay, so mating, assuming that the centers can be mated, then this quasi-conformal massage argument gives a map from the product of these into the, let's say, this space of normalized rational maps. And you could ask, well, surely this extends continuously to the closure. Why? Well, I mean, after all, this up to a Riemann map, this is just a copy of the disk. In fact, the Riemann map is just given by looking at the attracting multiplier. And this is just a copy of the disk. And so this component cross this component, that's a disk cross the disk. And surely the closure is canonically isomorphic to the closed disk cross the closed disk. Except that sometimes it isn't. Except that sometimes it isn't. In fact, it isn't precisely in the case, well, I mean, there's a topological criterion for it. It isn't precisely in the case when the mating that you find of the centers has, what should I say, has a basin contact between, I should have drawn these two different colors. I've got the black basin, I've got the red basins down here, and I've got the white basins up here. And if in the process of this collapsing, this somehow ends up touching this in a particular way, then that makes this impossible. In fact, the product of the closure of the product, what am I trying to say here? I didn't say this properly here. There's a hyperbolic component over here. Okay, so there's an isomorphism here. This is the mating map, which is an isomorphism, and this is canonically isomorphic to the disk across the disk. And then the question is whether this closure here in the space of quadratic rational maps, whether this map here is a homeomorphism. And there are examples where it's not, the ones I've discussed here. If these two basins of different colors end up being smashed together at the right point, then actually the closure here is not naturally the closed disk cross the closed disk, but it's this blown up in a particular way at a particular corner point. If the two periods are the same, then the point 1, 1 in these coordinates on the boundary is problematic, and this will have to be blown up precisely when these two different colored basins touch at internal angle 0. And this can be seen explicitly in the period 1 case, and if you work hard enough, you can see it in a few other low period cases. So that, once all is said and done, that's maybe not too surprising. So Jack has been studying this sort of thing in this family and other families in terms of his tameness conjecture. This blow up here, once you know how to do it, is not particularly difficult, and what you have here is still a semi-algebraic set, so it's not so bad. Okay, so that's one mechanism for discontinuity. And this mechanism doesn't even require you to run through many different hyperbolic components. It's really just about the product of a pair of hyperbolic components. Okay, and the other mechanism, well, okay, I have a little bit more time here, but not that much. So I want to show you 1.5 other mechanisms, and these will be combinatorial. Combinatorial in the sense that one can see, just by looking at landing patterns of external rays, by looking at sufficiently many examples made in a particular way, that you cannot have mating discontinuity. One way, which I'm particularly fond of, is, I don't have pictures of this now, but I can, well, here's some more pictures. Now these are pictures of Xavier Bouffe. These are slices. This is a space of quadratic rational maps, actually with labeled critical points, where you have a parabolic fixed point of some given multiplier, so some root of unity, and here the root of unity, this is probably 1/10. Okay, so these parameter spaces have been studied by many people, for example, by Eva Ur. And if you know where to look, you can see the image of a distorted Mandelbrot set that's had some part become unbounded, actually that in its mirror image. And then you see these lemniscates marching in, and then those yellow dots are just superimposed artificially so that you pay attention to those lemniscates. Those lemniscates are where you have degenerate parabolics. Okay, that's what I'm alluding to when I talk about what might happen when these things pull together and these two basins touch. So separately from this algebraic issue here, there's something that you can see if you know a little bit of combinatorics. Actually, this combinatorics was investigated systematically in the thesis of Tom Sharland, my former student and current Stony Brook staff member and new father. Right, so okay, he studied it in the hyperbolic case, but there's a natural bijective correspondence to the parabolic case, and some days I prefer the one and some days I prefer the other. You could say, what is it that distinguishes one of those, the maps at one of those yellow dots to another one? After all, both of them have, each of them has a parabolic fixed point of a given multiplier, and actually because it's degenerate parabolic, you have both basins, or both basin cycles clustering at the same point. So you have to pretend that there's 10 of them here because I can't draw too many. So what I've drawn here is the petals. So the local theory tells you that there will be, that at the parabolic fixed point it looks like this, and you have, let's say the rotation number is 1/4. So you know that you have this dynamics here, but of course one of these basins has a critical point, and one of these basins has a critical point, and there's a combinatorial separation. I mean, at least conceivably, these two could have been adjacent, or they could be separated by this much, or separated by this much, and one can prove that for every possible combinatorial separation except directly adjacent, there is one and only one example up to Mobius conjugacy, that these invariants, the rotation number and the displacement, that gives you a complete set of invariants. And in fact, now this hasn't been proved, but it's somehow implicit. It hasn't been explicitly stated, but I think it's implicit in Eva's model. In fact, as you march along, what you're doing is you're just cycling through, going from minimal displacement, next minimal displacement, so on and so forth. And sitting out at infinity are the obstructed cases where you have an adjacency. Okay, so I haven't said anything about matings here, but the other observation that goes into this is that one way to make these, if you want to prove an existence theorem, you have to somehow furnish an example, and you can make examples by matings, by mating a suitable rabbit, or a fat rabbit, because I'm in the parabolic case. So your rotation number essentially amounts to a selection of one of these components, and that's going to have these two associated angles here, and then you just play a game where you take these angles here and you do angle doubling in parameter space. This is the sort of thing that a priori you're not supposed to do, but you do it anyway. So you look at where the images of these rays under angle doubling land, and they land in various places, and that gives you a recipe for mating situations such that when you collapse, you get precisely this sort of picture. And just by inspection of the angles, you can work out what the combinatorial displacements are, and you find that you get each one exactly twice. And this is an example of what's called shared matings. And there's an equation I like to write down. So this goes back, a version of the first case of this goes back to Ben Whitner, the case of Q equals 3. FQ, all right, I've got a parabolic here, so let's talk about the parabolic ones. You can go back and forth between these by pinching argument of Peter Hazinski and Tonley and Swee, right? So FQ is the root of the 1 over Q limb. GQ is the root of the last period Q component along the real axis. And HQ is the root of the unique period Q component in the minus Q minus 1 component. Okay, so, well here, let me do it for 3. So this is F3, G3, so G3 is the airplane, and H3 is Kokokopelli. No, sorry, let me do it for 4. I'm sorry. G3 is equal to H3 by coincidence, and that's an observation of Ben Whitner, and he proves it by something called the Whitner flip. And we prove this here in a different way by looking at the combinatorial invariance here. If you go to the next case, here's F4. G4 is the root of the Airbus component, and H4 is the root of Kokokopelli. Okay? So take this now and let's just apply wishful thinking and let Q go to infinity. So as Q goes to infinity, FQ goes to the cusp, GQ goes to minus 2, the tip, and HQ also goes to the cusp, albeit in a anti-diagonal way, which should make you suspect that there's something funny going on. But this would converge to the cauliflower line segment, and this would converge to the cauliflower and the cauliflower. And now all you need to know is that when you do this mating here, you're gluing a circle along a line segment, so you get a line segment, whereas here you're gluing a circle along what? Jordan curve along a Jordan curve, so you get a Jordan curve. In fact, the circle, and because the circle is not homeomorphic to the line segment, mating can't be everywhere continuous. Something has to have gone wrong. This argument does not show you what's gone wrong, but these pictures here, this was investigated in a paper of mine with Xavier and Jean École, where we applied some funny mix of arguments to investigate the limit. It's a little bit hard to see, but as the period, this is now period 20, and this is period 50. And what you see in the foreground here that's emerging is the foreground seems to be converging to what you get in the limit at 1 over 0. Sorry, at 0 over 1. Well, whatever. In the limit where the rotation number is 1, and you do see that here, but you see all this extra stuff, all these extra enrichment decorations, and we were studying these decorations and trying to show various properties of them. And then another somewhat more, natural approach perhaps by double parabolic implosion. Yes?
So she told me to tell you.
Yeah, okay, I know, and you're using up my, so I'm gonna, yeah, all right, and I know, so we're gonna continue. Right, so, except you asked me a question before, so I'm gonna, right, so, there are other ways to investigate this besides the way we did, but the upshot is there's all of this structure here that tells you not just that this limit can't be the same as this limit, but you can actually start to inquire what the limit actually is. Okay. And finally, I did say something about magic formulas, and I haven't actually given the magic formula. This was supposed to be the point of the talk, but I got myself distracted. But a variant of this idea, in fact, it turns out, so I've been playing around with this, And then I heard about Duodé's magic formula, and when I went to learn about Duodé's magic formula, it was by and large what I had been groping towards, except it had already been observed by Duodé and discussed nicely in the thesis and publications of Camille Blay. Well, one paper by Blay and one paper by Blay and Valdez. And Duodé's magic formula is about the following remarkable observation, which is trivial to prove when you know it, which is that if you take any ray that lands on the main cardioid, there's two cases, there's the rational case and the irrational case, and you apply the magic formula. What's the magic formula? It's a real anticlimax. This is the magic formula. Probably if I want to use it in this presentation, I should just look at the ones landing on the top here, that the images of all of these, well, land somewhere on the real axis. So Wolf Jung made me a picture of this. I am coming to a close here. These are well, no, this is actually of a slight generalization here. So the image here, it's a rather sparse set. In fact, it has to be Hausdorff dimension 0, I guess, right? So anyhow, you get a rather sparse set of places along the real axis, but they are along the real axis. And then you can say, well, what happened? And in fact, they did say, this was, I think, the motivation. Suppose you mate, so this is, say, this would be 1/2 plus 1/4 theta. Suppose you mate this with this. You need to know the matings exist. You either prove that, which Blay did, which involves some work in the irrational case, or you just work with the, it's suitable irrational cases, or you just work with topological models. And you consider those matings. And once you do that, there's something evident that follows from the combinatorics when you just draw the combinatorics of ray landing for polynomials. And you find that in the rational case, the mating that you obtain has a certain critical orbit relation. This is just by looking at the picture. And in the irrational case, the matings have a different critical orbit relation. So this is a critical point here. So in the irrational case, one critical point maps after two iterates to another and then continues. And in the rational case, one critical point maps after two iterates to the parabolic fixed point. And this locus and this locus are evidently not the same. In fact, they don't even intersect. And the upshot is that in the rational cases, you have a collection of points that's suitably dense along some closed curve, some closed curve on this locus, on this algebraic curve here from this critical orbit relation. And in the irrational case, again, there's sort of the complementary dense set of points on the other one. And the graph, if you like, of the mating operation, it's like the characteristic function of the rationals. It's that kind of a pathology. So this follows by inspection once you know Duodé's magic formula. So my closing remark is that I got so intrigued by this, I decided to see if I could generalize Duodé's magic formula, because then I would find other sites in M cross M where this type of pathology here happened. And what I'm doing here is the easy part. It's the symbolic dynamics that supports this conclusion once somebody has proved that the relevant matings exist, and that is going to be work in the irrational case. The rational case is done already. So let me just close. And while I was doing this, Carlos Cabrera and Gamaliel Blay were pursuing a complementary generalization, and at some point we should try to put them together. But I'm just going to illustrate here. I guess I don't really have time to show you how, I prove this, but I'm going to show you the formulas. All right? I hope it's right. I mean, there's a recipe here. I mean, the talk I was supposed to give was supposed to be illustrating how to get the recipe here, but it's almost given by this here. So essentially, if you want to know the magic formula for, say, the rabbit component, that's line 3, I take the binary expansions of the two angles landing at the root, or rather the periodic blocks, And then I take the larger one followed by the smaller one. So I have 0.010001. And then I inquire, where is the best place to shift the binary point, the decimal, whatever, the period, so that what I get is closest possible to 1/2. And that yields that formula right there. So that's the generalization, and I'm done.
In the interest of companies for lunch and dinner, I'm told, we're going to phone questions.
In the interest, you won't ask any more questions.
Yeah, no more questions, sorry.